Hello everyone, welcome back to your online classes. And yesterday we have already learned the dispersion and refraction through a glass prism. A number of common examples can be observed in our day-to-day life for the refraction. A lot of phenomena in the nature can be explained by the atmospheric refraction of light, and some of them we are going to see. We might have observed that when we see a distant object through the hot air above the fire, we may see object seen through the hot air is fluctuating, and as we already know that the hot air is less dense. So the hot air above the fire will be less dense than the above, as the physical conditions of the air refracting medium, that is the air, not constant. The relative position of the object as we see through the hot air will be fluctuates, and this leads to the wavering, the flickering of the objects. The wavering thus an effect of the atmospheric refraction of light as we see through the hot air, that is the refracting medium. Then another example we can explain by the atmospheric refraction is twinkling of stars. When the starlight enters into the refracting medium, that is the air, as it passes through the air to reach our eyes, then as it passes through the different layers of air that has different refractive indices, and as it passes through this each layer, the starlight gets refracted. Since the atmosphere bends the light towards normal, that means the atmosphere bends the light due to refraction, and the refraction takes place gradually through the different layers of atmosphere that have different refractive indices. So the apparent position of the object, that is the star, changes than its actual position as we see the stars. The apparent position of the stars keep on changing as light passes through the different various layers of the atmosphere. Since the stars are very far away, when the light reaches our eyes, then the starlight might have undergo a multiple refraction to the various layers of the atmosphere. So the apparent position of the stars fluctuates, and we see the stars are a little above than its actual position. And as the starlight enters into our eyes, the position of the stars keep on changing, and that provides an effect of flickering of the stars or twinkling the stars. Then why don't the planets not twinkling? Planets are much closer than the stars, and thus are seen as extended sources. If we consider a planet as a number of point-sized sources of light, the amount of light entering from a point-sized source of light will average out of 0, thereby nullifying the effect of twinkling. Advanced sunrise and delayed sunset. The sun is visible to us 2 minutes earlier in sunrise and 2 minutes after the sunset. And this is because of the atmospheric refraction of light that coming from the sun during sunrise and sunset. And the time difference between the actual sunset and the apparent sunset will be 2 minutes. And the apparent flattening of the sun disk at sunrise and sunset is due to the same phenomenon. Next is scattering of light. The interplay of light with several objects around us gives us a number of spectacular phenomena in nature. The blue color of deep sea and reddening of sun at sunrise and sunset are some of the wonderful phenomena. And in previous class, in class 9, we have already learned that the scattering of light due to colloidal particles, and when the light is scattered by colloidal particle, the beam of light can be visible, and that enables us to see the path of the light to a true solution, and where the scattering of light can be visible through the colloidal particles when the size of the particles are comparatively larger. And one of the most important phenomena by the scattering of light is known as Tyndall effect. And the atmosphere of the earth is a heterogeneous mixture of particles. And these particles include water droplets, colloidal particles, minute particles, dust, foam, soil, and etc. When a beam of light strikes on such particles, the particles scatter the light and the path of the light will be visible. And this effect is known as Tyndall effect. The Tyndall effect is very commonly can be observed when the light comes into a dense forest. Then the path of the beam of light is visible, or the path of the light is visible as it passes. Again, when the light is coming into a smoky room, then the path of the light will be visible as the particles present in the room scatter the light. These are the examples of Tyndall effect. And this scattered light may be appeared as various colors, and the color of the path of the light depends upon the size of the particles present. Very minute particles mainly scatter the light into blue color, while particles of larger size may scatter the higher wavelength of lights. Then the scattering light may even appear as white. While the color of the sky is blue, the atmosphere have the size of the particles present in the smaller wavelengths of light. These are more effective in scattering the lower wavelengths of lights, like blue end of light, than the light of higher wavelengths like red color. Thus, when the sunlight passes through the atmosphere, these fine particles present in the atmosphere scatter the blue light than the red light, and so the blue light enters into our eyes, so the sky becomes visible as blue. The sky appears as darker for the space travelers as there is no scattering take place in the space at such heights. The color of the sunset is normally observed as red color. Since the sun is very far away from us, the light coming from the sun has to travel a large distance horizontally through the atmosphere. The wavelengths of the other colors are lower, and all the other colors are scattered, and only the red color will be able to reach or enter into our eyes. So the sun is visible as a red color during the sunrise and sunset. And this is all about the atmospheric refraction of light, and by which we can explain some of the natural phenomena we observe around us. I hope all of you understand. Thank you.